So hello guys, today we are going to discuss this problem, search in 2D matrix. So the question is something like this, that we are given IM cross an integer matrix having two properties, that each row is sorted in a non-descending order, that is in ascending order, and the first integer of each row is greater than the last integer of the previous row. That means this first element of this row will be greater than the last element of the previous row. Similarly, as this 23 is greater than 20, and if we have more rows, the first element will be greater than the previous element of the last row. Then we are given a target, that is 3, and we have to find that whether target exists in a matrix or not. So if it exists, we have to return true, otherwise false. There is one more condition, that we have to solve this problem in OM log of mn complexity. So one straightforward way can be, we can go in a matrix from 0, 0 till last, and we can find that whether the element is present or not. But that will be of mn complexity if the number of rows is m and columns is n, but we have to do it in log of mn. So this is simply a binary search problem because all the elements are in ascending order. That is, this is a sorted array. So what concept we are going to use is, instead of matrix, we are going to consider this as a linear array. So let me go on to the auto draw. So here we have this matrix that is 3 rows and 4 columns, and we will be considering this as a sorted linear list. And since we can do binary search in a sorted linear list, we will be performing the similar operation here. So what we'll do in place of when we do a binary search, we take a left. Here we'll do it as 0, and we take a right. So for right, we'll take it the element as 60, that is at element 2, 3, second row and third column. So how we'll derive it? We'll do rows into columns minus 1. So here we have 3 rows, 4 columns. So we'll have 12 minus 1, which will be equal to 11. So, and if we think that these are the indexes 6, 7, 8, 9, 10, and 11. So we are at right and at the left. As we do in binary search, then uh, we will do our binary search till left is smaller than right. And in every binary search, in every iteration, we will find a mid. Mid will be equal to left plus right by 2. So in this case, our mid will be equal to uh, it will be equal to 11 plus 0 by 2, which is 11 by 2, which will be 5. So we are at this element, that is 1, 1. So in order to convert this mid index to the element, what we'll do is, we will have row is equal to mid divided by columns, and column of this mid element, that is this 1 and 1, we'll have mid remainder operator columns. So here our mid was 5, our columns were 4, so 5 by 4 is 1, and here 5 mod 4 is also 1. So we have an element which we will which we will represent using matrix, row and column, right? We got the element. So now as we do in binary search, that if this element is equal to target, we are good, we'll return true. Else if um, this element uh, else if this element is greater than the target, that is since our target is 3, we found 11, so this is greater than target, we have to take our initially this was our left and this was our right, we have to shift our right to the mid. So we are at here, which will be equal to right is equal to mid, and then again we'll do a binary search. And if uh, if the case is that we have a element which is greater than 11, so what we'll do, we'll have our left is equal to mid plus 1. So the main logic here is this, that for the binary search, we are going to derive the row and column of our element, mid element, using mid divided by columns and mid mod columns. So this like we can convert, or we can translate a 2D matrix element into a linear matrix element using this formula. So this is the main concept, right? And the time complexity for this will be O of log of OMN, because the binary search works in a binary tree search fashion. In every step, it divides the tree into half of it. So let's quickly look into the code. Mm. So we have taken rows and columns. So row is the length of matrix, which is all the rows, and the length of the first matrix or the first row is our column. And the right, as we have seen, that it is row into column minus 1. Then we are going into a while loop. We are calculating mid as equal to left plus right by 2. So we are taking a floor division, because in floor division 15 by 2 will give 7, but in actual division it will give a floating point. But mid will be an index, we cannot have a floating point number. Then, as we have seen, that this is the main formula, row will be equal to mid floor columns, and column of the mid element will be equal to mid um, remainder operator columns. So if the mid element is equal to target, we are returning true. If the mid element is greater than the target, then we are shifting our right to the mid, that is, we are shrinking towards the left. Otherwise, if the element is greater than the mid, we are going on to the right side of the search. So we are shifting towards the right. And finally, if the target element is the very last element, we can return true, otherwise we'll be returning false. So this code actually works on log of OMN complexity. I'll be providing three codes, C++, Python, and Rust, into the video description. Thank you. Have a good day.